Yeah, please.
Okay. Well, thank you very much, Devira. I appreciate very much the invitation, and I've been looking forward to being able to tell you about some of the work that my group is doing. So the talk is going to be split into two sections. Part one is on devices that we're making with undoped gallium arsenide, which is, a fairly unique platform. Just a few other groups have worked on it. So I'll describe how it works and how we can realize lateral p-n junctions, single electron pumps, and ideally we want to put these together to make a novel type of photonic source. And then the second part of the talk is on the effort to build a quantum computer in silicon. Ultimately, you'd like to leverage the maturity of the silicon CMOS electronics industry. So I'll talk about our particular approach to scaling up, which is based on a network of nodes architecture. It's a little bit, outside of sort of the mainstream thinking on how you would scale up. So, but I think it's an interesting option. So I'll tell you about how that works. I'll touch on the idea of electron shuttling and discuss error threshold estimates. And then I'll briefly discuss our experimental work in this direction, though I expect this will probably be a bit abbreviated in the interest of time. I sometimes tend to try and cram too much into a talk, so we'll see how it goes. Okay, so the idea of the lateral quantum dot and the two-dimensional electron gas will play an important role in this talk. So let me just start by introducing them, particularly for those who may not be familiar. So a quantum dot is a zero-dimensional object. It's a very tiny conducting island on which we can confine charge carriers. At this scale, quantum effects dominate, and so we can't simply treat it as a classical charge distribution. And, for example, there will be an integer number of charges on the dot. Now, before we can form a lateral dot, we first need to form something called a two-dimensional electron gas, or TWDEG for short. So a very well-known type of TWDEG is formed at the interface of gallium arsenide and aluminum gallium arsenide, or I'll call them gas and algas, sort of for short. So a stack of materials like the one I'm showing here is known as a heterostructure and can be grown by molecular beam epitaxy, atomic layer by layer. So when a layer of dopant atoms is placed appropriately, so here in this diagram, these plus signs, then the dopants donate electrons, and the electrons will naturally accumulate where the potential energy is the lowest. So now if we plot the potential energy as we move down vertically through the structure, we'll find that there's a quasi-triangular quantum well that forms right at the interface of the algas and gas layers. So the electrons accumulate there, and this gives a very thin, only about 5 nanometer thick, two-dimensional sheet of electrons. So that's our TWDEG. Now, to form a dot, we need to further confine carriers within the plane, and that can be done electrostatically by placing metal electrodes on the top surface. Okay, something like we're showing in this cartoon here. So we call these metal electrodes on the top gate electrodes. So by applying voltages to these gates, we can shape the underlying potential energy landscape. So in particular, we can make it unfavorable for electrons to be in certain locations by raising the potential energy above the Fermi energy. So now with a suitable gate layout, we can form one of these quantum dot islands, or multiple dots, whatever we want, and we can have the quantum dot be tunnel coupled to electron reservoirs on either side. Now, if you recall from your solid state physics course, the density of electronic states, I should say, as a function of energy, has a different form for conductors in different dimensions, right? So in 3D, it goes as the square root of energy. In 2D, it's actually constant, but because you can have different subbands, multiple subbands, you can get this kind of staircase shape. In one dimension, it goes as 1 over the square root of E, but again, you can have multiple subbands. And then in 0D, which corresponds to a quantum dot, only discrete energy levels are allowed. So that's a key thing to keep in mind. Now, the spacing between these levels in a quantum dot is due to two things. One, the energy of Coulomb repulsion between electrons, and two, the quantum mechanical orbital energies, or in other words, the particle in the box energy spectrum. Okay, so now if we look at the energy diagram for a generic single quantum dot connected to left and right electron reservoirs, so that it would look like this picture here at the lower right. So in the leads, we have electrons filling a continuum of levels up to the chemical potential, mu L and mu R, standing for the left and the right chemical potentials. Now in the dot itself, the energy levels below the chemical potential are filled, just like they are in atoms, with 2 electrons of opposite spin. Now is probably a good time for me to mention that experiments on this kind of quantum dot can only be done at very low temperatures. This is because at high temperature, the Fermi distribution, which describes the density of states in the reservoirs, gets smeared out so much that you can't distinguish individual levels in the dot by measuring the transport of electrons from left to right. So we need to be at low enough temperature so that the level spacing is larger than KT, right? So the width of the Fermi-Dirac distribution is of order KT. And we can only really distinguish the discrete levels in the quantum dot if KT is less than the spacing between those dot levels. So the energy spacing in a quantum dot is typically on the order of milli-electron volts. So that means that we typically need temperatures below 1 Kelvin. These are the kind of temperatures that you can achieve in a helium-3 cryostat or a dilution refrigerator. Okay, so now what would happen if we remove the dopant atoms from the heterostructure? So at first, this maybe sounds like a silly thing to do, because then you wouldn't have the donated electrons to populate the 2-deg. And if you don't have any applied fields, you don't even have a confining potential for a 2-deg. But it turns out that we can still form a 2-deg. We just need 2 things. One, we need a global top gate to provide an electric field that can be tuned to make a confining potential at the gas-Al-gas interface. Okay. And secondly, we need what's called a recessed metal ohmic contact to the 2-deg, which we show here in this diagram. In other words, this is like a side contact that provides a low resistance path for electrons to fill the 2-deg. Now, conventional ohmic contacts won't work because the top gate here would be screened by the metal at the surface. So you would get a discontinuity, and the metal contact would not be continuous with the 2-deg. So the recessed ohmics must have this particular slanted profile, which forms when the metal is annealed and diffuses laterally. Now, to obtain high quality ohmic contacts in this configuration is very tricky. A lot trickier than for the standard modulation dope samples. And that's why not many groups work on this. It took us a couple of years to really perfect this, but you can do it. And I think the effort is worthwhile because we gain some clear advantages over the standard doped material once we can do this. So what kind of advantages? Well, the first advantage is higher mobility and better device reproducibility. So here's a comparison of the electron mobility measured in experiments versus electron density for 2 heterostructures that are nominally the same, except for one being doped and one being undoped. Now, let me first say that mobilities in the conventional doped heterostructures like this are already very high to begin with. I mean, if you look at the mobility in centimeters squared per volt second, it's already in the range of over a few million. And so, of course, that's already a very high mobility. The reason we can achieve that in these structures is because the interfaces are very high quality and because the dopants are spatially separated from the 2-deg. And that reduces scattering compared to a uniformly doped semiconductor. Okay, so that's why these are referred to as high electron mobility transistors or HEMT structures. However, without doping, we can see that the mobility is actually higher in this region of lower carrier density. This is actually not surprising since the dopant atoms act as ionized defects and are a dominant source of scattering. So, removing the dopants decreases the scattering. On the other hand, when you're at very high carrier density, up here in the upper right of the plot, electrons in the 2-deg screen each other from the ionized impurity potentials. And so in that regime, we don't see much difference between doped and undoped. Okay, so the lack of dopants also tends to make devices more stable and reproducible from one cool down to another. The dopants and related crystal defects are a source of charge fluctuations, typically have something like a 1/f noise spectrum. And in any one particular cool down, you usually freeze in some sort of random charge configuration. But if you don't have dopants in the structure to begin with, these charge fluctuations and frozen in potentials are very much suppressed. So it's a cleaner system in many ways. Now, the second very important advantage of the undoped heterostructure is that now we're not limited to just electrons. By applying a negative top gate voltage, we can instead induce a whole gas. So, now there's a bit of a challenge because the ohmics, the metal ohmic contacts for holes must be made from a different combination of metals. So we use gold beryllium. And so therefore, you need separate N-type and P-type ohmic contacts. But other than that, it really is just as simple as changing the top gate voltage to get electrons, an N-type semiconductor, or holes, a P-type semiconductor. So, that means that we can make truly ambipolar devices with these gallium arsenide 2-degs and 2D hole gases. And that opens doors to a lot of exciting things. So here's an example of a lateral p-n junction. This is an optical image of a device that we fabricated at Waterloo. So in gold, you can see the top gates on both the left and right. And you can see that they overlap with both P-type ohmics and N-type ohmics. So I've kind of labeled them here. So that means that both sides of the device can be either N or P. So we can have any combination that we want. We could have NN, PN, NP, or PP. Okay, and now if you look at this N set, this shows that near the junction gap, so we're making a, say we want to make a PN junction. This is the gap where we've sort of tapered down to it here. The top gate in that region is just a very thin 5 nanometer thick layer of titanium. And we did that so that the top gate would be transparent so that we can see electroluminescence. Okay, so say we apply a sufficiently negative top gate voltage on the left side, that's going to induce a 2D hole gas. And then a positive voltage on the right side induces a 2D electron gas. So this would give us a PN diode. In order to overcome the barrier, the diode barrier, and get current, we need to apply a bias voltage on the order of the band gap of gallium arsenide, which is about 1.5 volts, right? The band gap in electron volts is about 1.5. Okay, now if we switch the top gate polarities, we would get an NP junction. And if we wanted to see current through that, we would have to reverse the polarity of the bias voltage to get a current. Okay, and so here, for a device similar to what I just showed, this is experimentally the diode behavior, bidirectional diode behavior. So the green curves, let's look at the green curves first. That shows the IV behavior of the PN diode. So note that the current for the green curve remains 0 on the left side of the plot. So for negative biases, you never get current, but only at around 1.5 volts, you see a sharp turn on for the PN diode. And that's exactly what we expect to see a turn on around 1.5 volts. However, the dashed green curve here is what we get on subsequent traces. Okay, and so we attribute that to a change in state of the device, probably due to charge accumulation somewhere in the device. This is something that we're still, working to understand. We don't fully understand it. But if we switch the polarities, then we would get the red curves here. And we can see that we indeed get an NP diode in that case. And everything looks pretty symmetrical, both the initial sharp turn on as well as the more gradual turn on that we see after subsequent traces of subsequent IV traces on the device. Now, interestingly, it's even possible to operate the diode in an AC driven mode. And what I mean by that is alternating the top gate potentials so that you can alternate between PN and NP configurations. So if the bias voltage is kept fixed, say, positive 1.5 volts or above, then you can only get current during the PN portion of the cycle. During the NP portion, you would get no current because the diode would be off. Okay, and so that's what we see in this plot. Now, the on-state current was observed to be somewhat stochastic. You can see that by the range of variation of these gray single shot measurements. But the overall trend is still consistent with the diode that turns on at the expected bias voltage of 1.5 volts. So the reason this AC driving is interesting for us is because we find that it actually stabilizes the device for electroluminescence experiments, because it prevents excessive charge from building up on either side of the device. Now the data shown here is for a very slow alternating AC frequency. But we can also, we've actually been able to do this up to roughly 1 kilohertz. So we can actually, swing the top gate voltages from +5 to -5 volts and do this AC driving up to 1 kilohertz, which is pretty fast. And that's really just limited by the parasitic capacitance of the device. Okay, so moving on to talk about electroluminescence, my colleague Mike Reimer here at Waterloo has a photonics lab with an optical cryostat. So together with him and his postdoc, Lin Tian, we've collected electroluminescence data from these devices. Now, I should say that I'm not an optics expert myself, but given the interest and the strength that you have at Toronto in quantum optics, I thought I would speak a little bit on this aspect of it. So we observe emission at the expected wavelength around 820 nanometers, which is the band gap, or corresponds to the band gap of gallium arsenide. Now, before going further, I need to mention that there are actually two types of heterostructure that we have used. The first I've already talked about, where you have a single gallium arsenide, aluminum gallium arsenide interface. We call that a single hetero interface. The other is a quantum well heterostructure, where you have a thin layer of gallium arsenide that's sandwiched in between two layers of aluminum gallium arsenide. Now, in the quantum well heterostructure, electrons and holes are always confined to the quantum well. So it's natural to expect that when we force electrons and holes together in a p-n junction, we can form excitons, and those excitons can radiatively recombine and emit light. However, for the single hetero interface, this is not at all obvious. And the reason is that in the gap between the top gates for a single hetero interface, there's actually no confinement for electrons or holes. Nonetheless, we still observe electroluminescence from these devices. And I think we're the first people that have ever tried that, actually. In fact, the spectrum that I'm showing here is from a single hetero interface device. Now, this might be because the carrier mobilities are very high. And so even without confinement, because the carriers move ballistically, you still get significant exciton formation. Now, the other remarkable thing about this is that the emission spectrum is quite narrow. In this particular spectrum, we see that the spectrum is dominated by a single peak, which we ascribe to the neutral exciton. and the line width is about 1 millielectron volt. This particular device had a 3 micron gap between the top gates. Now, when we sort of zoom in on one of these spectra, we typically see more complexity, and we can fit several overlapping peaks. And some of those peaks may correspond to charged excitons. Some of them may correspond to defect states. We're still working on the details of that. Now, the narrowest neutral exciton peak that we've observed was about 0.4 millielectron volts in width, which is really, really narrow. We think this may be one of the narrowest observed in the literature. And we think that it's the high quality of the heterostructure material and the lack of dopants that are part of the reason for this. Now, in some experiments, interestingly, we observed 2 well-separated peaks, which we tentatively label as X0 and X minus, neutral and charged excitons. The X minus is at a lower energy or higher wavelength due to the binding energy of the additional electron. So interestingly, we can actually influence the spectrum based on the induced carrier densities in the N and P regions. So if we make the top gate voltages asymmetric, so that there's a higher hole density compared to electrons, we can almost remove the charged exciton peak completely. Okay, so that corresponds to this asymmetric top gate condition here. On the other hand, if we have a higher electron density compared to holes, we can keep the X minus peak and nearly remove the neutral exciton peak, showing here. So this is still tentative. I mean, we haven't published this yet or anything, but it's an interesting aspect of these devices that we want to explore further. We can also drive the electroluminescence in a pulsed fashion at radio frequencies. So here in the upper left is a newer generation device that we fabricated recently. And it has an etched channel, and still you see the p-n junction with the thin titanium top gates that have kind of a green translucent appearance. Now, we've added additional barrier gates in this device, and those are to prevent carriers from recombining outside of the central area of the device. Now, as we see in this circuit schematic here, we can apply a small RF signal on top of the DC bias voltage across the device using a bias T. If we adjust the DC bias to be just below the threshold for light emission, and then we apply an RF pulse on top of that, when the RF pulse adds to the bias, then we exceed the threshold and light is emitted. Emitted photons are detected by a single photon detector, here this SPD, which then sends a signal to a discriminator, which is kind of like a timer that gives us start-stop measurement. Okay, so when we do this and we accumulate over many cycles, we get a histogram like the one shown here in the lower left. So here the RF waveform that we were sending is just a square waveform that's on for 1 nanosecond and off for 9 nanoseconds. So the total period is 10 nanoseconds with a duty cycle of 10%. Okay, but rather than seeing square pulses, we actually see sort of more Gaussian shaped pulses. And that's actually entirely an artifact of the waveform generator that we used. The waveform generator had a bandwidth of about 300 megahertz. And so in fact, the pulses coming out of it were Gaussian to start with. But you can see that that the peak, the electroluminescence peak that we detected is a little bit asymmetric. There's a tail here on the right side. And that tail is because of the finite lifetime of the excitons. You know, gives a decaying exponential that's kind of convolved with the Gaussian shaped pulse. So from detailed fitting of this line shape, we estimate an exciton lifetime of about 280 picoseconds. Now this is quite a bit shorter than the exciton lifetime that we measure using photoluminescence on the same heterostructure. But with photoluminescence, electrons are excited well above the gap, and they have to first relax to the conduction band minimum before they recombine. Whereas these electroluminescence experiments are performed close to the conduction band edge. And so that might explain why the exciton lifetime shorter there. In any case, this shows that we can achieve light emission with very good timing resolution. And that's potentially interesting for quantum sensing and ranging. Now, for quantum optics, we'd like to have a source like this, but for single photons. Okay, and so for that, we need to turn our attention to single electrons. Okay, and so now I'm going to introduce the single electron pump, which you can think of as a dynamic quantum dot. What we'd like to do is controllably inject a single electron into a p-n junction at a relatively low momentum so that it's likely to radiatively recombine with a hole and emit a photon. So a device called a single electron pump can do that. The idea is to form a dynamic quantum dot. Here I'm schematically representing a 1D potential that's, you can think of as just a 1D cross-section of a dot potential. This is a dynamic potential because at least one of the gate voltages controlling the potential is being varied at high frequency, hundreds of megahertz, even up to a gigahertz. Now we can split the cycle into 4 parts. The first step is loading, where you lower the left tunnel barrier and essentially scoop up electrons into the dot. Then in the second step, you start to raise the left tunnel barrier, and in that process, some electrons tunnel back to the left reservoir. As you continue to raise it, you define a dot with a strong confining potential and a small number of electrons in it. And then as you raise that left tunnel barrier even further, you create this kind of potential which kicks one or more electrons out of the dot to the right side. Okay, now, there are several variations on the idea of an electron pump or electron turnstile. But this one that I've presented is conceptually the simplest one, and it's called a 1-parameter pump, since only one tunnel barrier is dynamically varied. Okay, and this is the kind of pump that we've actually realized experimentally. So if you look at this diagram on the top, this is a top view of the device, sort of looking through the top gate down to the gates on the surface. So you can see these local gate electrodes in gold. The U-shaped ones together form a 1D constriction, a 1D channel. And then the 2 vertical gates that I've labeled V entrance and V exit form the tunnel barriers. And so what we're going to do is we're going to apply the RF voltage, RF plus a DC voltage, to the entrance gate and vary that left tunnel barrier and hold the V exit fixed. And that gives you exactly these steps that are shown schematically here. Now the bottom picture is a scanning electron microscope image of a pump device that we fabricated. Note that you don't see the top gate here because this image was taken before additional dielectric and the top gate were deposited, right? Otherwise you wouldn't be able to see these gates anyway. So when we make such a device and we properly tune it, what we can get is a quantized current. That means that an integer number of electrons are emitted per cycle. So if 1 electron is emitted per cycle, then the current is simply E times F, where E is the electron charge and F is the frequency of the RF signal that we're applying to the entrance gate. Now by adjusting the DC voltages on the barrier gates, we can emit 2 electrons per cycle or 3 electrons and so on. So the current for an ideal pump is quantized as N times E times F, where N is an integer. Okay, so here on the left, we see an experimental pump map for a device, pretty much identical to the one that I just showed you. So in the color scale, we see the differential conductance, which is the derivative of the pump current with respect to the DC voltage on one of the gates. So, by varying the DC voltages on both the entrance and exit gates, we can form this map of conductance versus those 2 gate voltages. Now, the bright lines indicate where the current changes abruptly, in other words, a step. And then the dark regions indicate a non-changing current, or in other words, a plateau. Now, if we take a line cut along a horizontal line like this, and now we plot the current, not the differential conductance, but the current, then we can clearly see the quantized plateau, the quantized current plateaus. Now the left plot is for an RF frequency of 500 megahertz. The one on the right is for 850 megahertz. Note that the current on the first plateau in both cases corresponds exactly to E times F for those two frequencies. And the second plateau is exactly double that current, and so forth. Now we can see that quantization is strongest for the n=1 plateaus and decreases at higher plateaus because the charging energy of the quantum dot tends to decrease as you move to the right. The first plateau can be fit to a model called the universal decay cascade model. And the yellow curves on top of the data here are actually fits to that model. Now we can roughly estimate what the error in pumped current is by taking just 1 minus the fit value at the inflection point of the first plateau. Okay, this is not a direct measurement of the error, but it gives us a way to get a good estimate of what the error would be if we actually carried out a very long high precision measurement. And so this gives us an estimated error of around 1.7 parts per million for the 500 megahertz pump. So that would mean that out of 1 million cycles, only an average of around 2 cycles would give you something other than exactly 1 electron. For example, 0 electrons or 2 electrons. Okay, this is just an estimated error, but it's already on par with some of the best pumps in the literature. Now, metrologists are interested in very high accuracy pumps because it's a viable route to a new and better current standard if the errors can be reduced by another couple of orders of magnitude. These pumps can also be used as sources in single electronics, single electron optics, and as I'll describe, for a single photon source. And then just briefly mention, we can observe well-defined plateaus up to around 4 Kelvin and close to 1 gigahertz pumping frequency. So this is just to say that we don't actually need a dilution refrigerator to see quantized charge pumping. We can actually see it at a few Kelvin. Okay, so now the idea is to combine the single electron pump with the same sort of p-n junction that I showed you before. So the pump is located on the inside of the p-n junction, and in each RF cycle, we can operate on the first plateau, for example, and inject a single electron into the sea of holes on the p side of the device. Now, since gallium arsenide has a nice direct band gap, the electron finds a hole and it can radiatively recombine, emitting a single photon. Moreover, we're not limited to the first plateau, and by varying the exit gate voltage, we could work at the second plateau. We can inject 2 electrons per cycle. The third plateau, we can inject 3 electrons per cycle, etc. Now, if radiative recombination were 100% efficient, this would translate to time-correlated pairs, photon pairs when n=2, photon triplets when n=3, and so forth. Of course, the radiative process won't be 100% efficient, but this is something that we're eager to make this device and study it and see what we can get. We expect to emit single photons with the same narrow bandwidth that we obtained in the EL experiments that I showed you earlier. Time-correlated pairs, if we can achieve that, are very interesting in that they would be a resource for quantum illumination, which is kind of a family of methods for doing quantum ranging, detection, and imaging at the single photon level. And you can do that either with entangled or time-correlated pairs. Now, I should mention that actually we're not the first to think of this, and an experiment was published last year by a group at Cambridge. However, instead of using a single electron pump, they used surface acoustic waves to inject single electrons into the p-n junction. So they were able to demonstrate single photon emission by measuring the second order correlation function, the G2, and finding that G2 of 0 was less than 1/2, which is kind of the threshold to say that you have a real single photon source. Now, surface acoustic waves are not quite as precise as pumps in terms of the error rate. So I think, this bodes well for our source. And so we're working on the pump-based device, and hopefully we can have, results to show on that soon. And here are a couple of preprints on undoped 2DAGs and the single electron pump, just in case, anyone is interested in further details. Okay, now let me turn to the second part of the talk on quantum computing and silicon. And I'll try to, I know that time is getting short, so I'll try to make this a little bit faster. So when it comes to quantum computing with spins or spin qubits and semiconductors, 3-5 semiconductors like gallium arsenide that I've been talking about earlier have the issue of nuclear spins in the lattice that you can't get rid of by isotopic purification, because all of the isotopes in the columns 3 and 5 of the periodic table have nuclear spin. For silicon, however, we can remove the 29 silicon nuclear spins and be left with a spin-free 28 silicon lattice. So this greatly increases the coherence times of electron spins confined in quantum dots, making that a good candidate for a scalable qubit system. So we can adapt the idea of the conventional MOSFET transistor, modify it a little bit so that it becomes a quantum dot at low temperatures. So again, we can use gates on the surface to accumulate a 2DAG, but now the 2DAG exists at the silicon dioxide interface for a MOSFET type device. And local fine gate electrodes can be used to define the quantum dots. Now, some groups use specially grown heterostructures in silicon germanium, where the 2DAG is confined to a silicon quantum well sandwiched between 2 layers of silicon germanium. But you can just think of that as another variation of the same idea. Other groups fabricate devices in conventional silicon foundries, like the one shown here from CEA-Leti in France. Our colleague here at Toronto, Professor Voinegescu, takes a similar approach, which I think is very promising. Whole spin qubits have also been demonstrated with the benefit that you can have efficient electrically driven single spin rotations because of the strong spin orbit coupling felt by the holes. Now, an obvious advantage with silicon is that you can leverage the maturity of the existing CMOS industry. And it's natural to think about co-integration of classical and quantum circuits on the same chip. Also, the operating temperature can be high relative to, say, superconducting qubits. Superconducting qubits really only work well below 100 millikelvin. Spin qubits have already been demonstrated to work at around 2 Kelvin, and in principle could work at 4 Kelvin or higher. State readout is really the challenge there. The higher temperature operation is really what opens the door to co-integration of classical control and readout circuits. And that's because the cooling power of a cryostat increases very rapidly with base temperature. So rather than only being able to handle microwatts of power at millikelvin temperatures, you can actually handle milliwatts to watts of power dissipation at a few Kelvin in principle. Okay, so the question that we want to ask is, how do we go from the laboratory scale devices we have today, like the one shown here on the left? This was actually one that we fabricated here at Waterloo. How do you go to a truly large scale processor? For example, one that's based on the surface code for quantum error correction. We know that the scale of the problem and overhead required is very staggering. To factor a 2000-bit RSA number, Fowler et al. In their 2012 paper estimated that you would need around 100 million physical qubits and 27 hours of runtime based on superconducting qubits with 100 nanosecond readout timescale. I mean, that's an extreme example, but even scaling to intermediate scales like hundreds or thousands of physical qubits will, of course, be quite challenging. So, people have started thinking about this, and there have been some proposed architectures. To directly map the surface code to a densely packed 2D array has some obvious challenges. density of wiring interconnects is very high. And so even with 3D integration, the conventional foundry processes can't reach this kind of interconnect density today, because quantum dots are very small, right? 100 nanometer scale. Then there's the issue of crosstalk, right? Gates capacitively couple to everything nearby, not just the dot that they're intended to control. And so this also means that controlling the exchange coupling of each qubit with 4 neighbors in order to do 2 qubit gates would be extremely challenging. Exchange, by the way, is the method for doing 2 qubit gates with spin qubits, with nearest neighbor spin qubits. And the exchange energy is an exponential function of the tunnel barrier, which makes it very sensitive to charge noise, control errors, and crosstalk, and all of those things. So more recent proposals improve on this in some aspects and start to rely on moving qubits around by shuttling, but they still aim for dense 2D arrays. So to boil things down to a very simple picture, a dense 2D array of quantum dots is hard, okay? And that's because at the scale of a quantum dot, which is 100 nanometers or less, for all the reasons I just said, it's difficult. You can certainly make an array, but to achieve the level of control that you need for universal fault-tolerant quantum computing, it's going to be quite a challenge. On the other hand, if you look at today's laboratory experiments, few qubit devices, a 1D array is a very common configuration. And we more or less already know how to do that with enough control to demonstrate algorithms on 2 or 3 qubits, for example. Scaling to larger 1D arrays is very feasible. Okay, so that's relatively easy. Error correction in 1D is very inefficient, though. That's the problem. So we really need a 2D code. So the question is, can we build a 2D surface code out of 1D quantum dot arrays? So I will argue that yes, we can. And the idea for this is based on a network of nodes approach that was first introduced by Simon Benjamin's group at Oxford in the context of ion trap quantum computers. And they were thinking about how you might utilize many small processors that can be somehow linked or coupled rather than building a single very large processor. So it turns out that you can actually map the surface code to a network if you can share entanglement between neighboring nodes. So at the beginning of each surface code cycle, you would entangle 2 qubits between neighboring nodes. In the case of ion traps, this could be done with a quantum optical link, for example. So once you have that shared entanglement resource between the neighboring nodes, everything else in that cycle can be done locally within the nodes. Okay, and there's a single data qubit in each node that holds the precious quantum information, and 2 or 3 ancilla qubits that are used for carrying out the stabilizer operations, which is the basis of the surface code. So in the original paper, they also showed that rather large infidelities in the entanglement distribution, up to 10% or so, could be tolerated. But this comes at the expense of needing additional ancilla qubits and operations to do entanglement purification. So, we had the idea to map this to a spin qubit processor. And I think a nice aspect of this idea is that you can then split the scaling problem into 2 parts. The ability to carry out local operations on these small nodes, which essentially we can already do. It's just that you would need to do it with global control lines. And then secondly, the ability to distribute entanglement between neighboring nodes. So here's a kind of cartoon of the network architecture mapped to a silicon processor as we originally envisioned it. So the nodes are small linear arrays of a few dots. The data qubit is shown here in green. I'm not showing the explicit gate electrodes to define the dots. This is just kind of a schematic. The quantum dots are initially filled by electrons that come from an ion-implanted reservoir. And those electrons are brought to the nodes by an accumulation gate, shown here in orange. The reservoirs don't actually need to take up so much space. Again, this is just sort of a sketch. Now, to distribute entanglement between nodes, the most straightforward way to do that is simply to move electrons around. Okay, and this is referred to as shuttling. And by that, we mean that you have a linear array of empty dots. You can fill one of the dots at the end, and then by successively raising and lowering the gate potentials, you can force successive tunnel events and push an electron through the array. And we can elongate those gates somewhat to stretch out the shuttling dots. And those are represented here by these blue structures, which together form what I've called the shuttle highway. So you notice that in this design, locally, all the dots are in a 1D array. But because of the ability to shuttle electrons, we can actually form an overall 2D array of connected nodes. And therefore, we can map the 2D surface code. And also, you know, we've made space for realistic wiring interconnect densities and also co-integration of components. Okay, you can adjust the size of the scale of this lattice to meet those constraints. So how do we get entanglement? Well, in a sense, we get that for free in quantum dots. When you fill an atomic orbital, remember, with 2 electrons, they form a spin singlet. And that's a maximally entangled state of the 2 spins. So it's the same for quantum dots. You can think of quantum dots as artificial atoms. So when we load 2 electrons into the ground state of a dot, then we can separate the 2 spins spatially by adjusting the gates to favor the 1-1 charge configuration, right? And I've kind of indicated that as a path in this charge stability diagram. So going from the 2 electrons in the same dot to 1 electron in neighboring dots, and you can preserve the singlet state as you do that. We can further separate the electrons with more shuttling steps to get a more and more non-local singlet state. Now, for electrons in silicon, the spin-orbit interaction is weak. And assuming the nuclear spins are removed as well, as I mentioned before, then it may indeed be possible to achieve coherent spin transport over micron scale distances. This is still a bit of an open question. Now, for the sake of time, I won't go into detail, but the Pettit group from Princeton demonstrated single charge shuttling over 9 dots, a 9-dot linear array, on a time scale of 50 nanoseconds. So that's around 5 nanoseconds per shuttle. And this was a nice experiment because it demonstrated that charges can be moved essentially 100% deterministically. Now, they didn't look at spin coherence in this experiment. This is just charge shuttling, but they showed that can work almost perfectly and deterministically. So, you know, this is not science fiction. This is a real thing that you can do. Now, each cycle of the surface code is called a stabilizer operation. And let me briefly walk you through how it works in this architecture. So we focus on a subset of 4 nodes. Singlets are loaded in nodes A and C to begin with. And entangled spins are then shuttled to nodes B and D, where they're stored as ancilla qubits. This is again repeated with nodes A and C. So now we've shared 3 singlet states. And from there, just using local operations, we can form what's called a GHZ state, which is a particular 4-qubit entangled state. And that spans all 4 nodes. From that GHZ state, and some additional operations within the nodes, we can carry out the stabilizer operation, which is the heart of the surface code. So this is exactly the same process, but in a circuit diagram notation. Time goes from left to right. The first 2 blocks are for the entanglement distribution. The 3rd block here is for the GHZ state preparation. And then the 4th is the stabilizer, which involves, you know, a control Z or control not gate. Now, these ancilla qubits labeled A1 are measured at the end of each cycle. The data is processed on the fly, and when an error is detected, corrective operations would be applied to the data qubits. Okay. So, you know, for the surface code to work and actually reduce the logical error rate, the physical qubit error rates must be below some threshold. So we can roughly estimate those thresholds if we have an idea of the kinds of errors that would dominate in a real device. So with our colleagues at Oxford, we developed methods for estimating the error thresholds for this architecture. Now, a nice thing is that we have the Gottesman-Knil theorem, which says that for stabilizer circuits, we can efficiently simulate them because they're constructed out of generalized Pauli operators, and those can be efficiently simulated. So this gives us the ability to simulate large codes and get the error rates. The problem with quantum dot processors is that you have exchange gates, and which we also refer to as swap or square root of swap gates. And those cannot be written as generalized Pauli operators. So we had to use a trick called twirling so that on average we could get, we could represent the swap error by Pauli operators. Okay, so then when we plot the simulated logical error rate as a function of the physical qubit error rate, we can plot that, and we can plot it for different code sizes. Where there's a crossover point, it means that below that physical error rate, increasing the size of the surface code decreases the logical error rate, which is what you want. So that crossover point is the threshold value that we want to identify. Okay, so these calculations, of course, depend strongly on the assumptions that you make, but assuming physically reasonable noise models, we estimate close to a 1% error threshold on dephasing errors during shuttling, assuming 2 qubit and 1 qubit gate errors that are, perhaps slightly better than state of the art, but certainly within reach. Okay, I know I'm running low on time, so this will be brief, but I'll just briefly mention some of our experimental work. These are MOSFET quantum dots using aluminum gate electrodes on top of silicon dioxide on silicon. The left is, here we see an SEM picture, and the right shows a simulation of the potential landscape for the same device geometry with certain gate voltages applied. Now, the lower device here is actually a charge sensor, and it's capacitively coupled to the upper dot. Note that in this structure, there are no explicit gates to control the tunnel barriers between the leads and the dot, right? L and R denote the accumulation gates for the left and right reservoirs, and P denotes the plunger gate for the dot. So the tunnel, there are no explicit tunnel gates here. So we showed experimentally that you can actually control the tunnel rates over many orders of magnitude based on the voltages that you put on the left and right accumulation gates, if you've designed the geometry properly. Okay, so for tasks like charge sensing or shuttling, you don't actually need a third layer of gates to control tunneling. And reducing the number of gate electrodes per dot is a huge benefit for scalability. So, so I think this is useful. Now, in the computational nodes where you need to do 2 qubit gates based on exchange, you would still need to have tunneling gates there. Okay. Now, in the same sort of device, we can look at the spin filling behavior through magneto spectroscopy. That means we look at the shift in energy levels that we measure in transport as a function of magnetic field that's applied. So here we see that the first electron that we fill in the dot is spin down, for example. The second electron is spin up, as you would expect. But at around 2.5 Tesla, the second spin crosses over to spin down, right? So we go from spin up to spin down. So what exactly is going on there, we might ask? Well, in silicon, you have multiple conduction band valleys. And in a 2-DEG, you end up with the 2 lowest valley states that are nearly the same in energy, but typically are split by a small valley splitting energy. So at 2.5 Tesla, the upper valley state spin up configuration, the upper valley state spin down configuration becomes lower in energy than the lower valley state spin up configuration. And so we get this crossover. So from that crossover point, we're directly reading off the valley splitting energy, which is in this case around 300 microelectron volts. So I don't have time to go into it, but the presence of these valley states is one of the main challenges for spin qubits in silicon. All right, we can also fabricate multi-dot linear arrays using the same type of layout. And what we would like to do in the future experiments is use a triple dot to characterize the spin shuttling process and determine, whether it's really feasible or whether things decohere too quickly during shuttling in terms of the spin state fidelities. Okay, so this is something we plan to do. And I don't have time to talk at all really about this. This would be a separate talk, but regarding, we also do a lot of theory and simulation work complementary to our experimental work. And we're actually developing an open source simulator for silicon quantum dots. And this is based on prior work we've done simulating shuttling and calculating exchange energies. So I'll just list the two papers relevant to that here. And if you want to ask about it later after the talk, I'm happy to discuss it. Okay, so that's all I had to say really. And so to summarize, we showed that in undoped gallium arsenide structures, we can get higher mobility, better reproducibility. We can make ambipolar devices. We can make lateral PN junctions that emit light, very narrow band electroluminescence. We actually made the first single electron pump in undoped gallium arsenide. Lots of them have been made in other systems, but this is the first one in undoped gallium arsenide. And we made progress towards a single photon source. And with the silicon processor, we proposed a network architecture for implementing a surface code that only utilizes linear dot arrays, gives space for co-integration and wiring. We introduced a simplified MOSFET design without tunnel gates that can be used for charge sensing or shuttling. And we showed Zeeman spectroscopy in a single electron quantum dot. Okay, and so with that, I would just like to acknowledge my group members and support from our funders. And I'd like to thank you very much for your attention, and I'm happy to answer any questions. And the last thing I'll do is I'll just put up this slide here to advertise a recent review paper that we put out that might be interesting to some people. It's a roadmap on quantum nanotechnologies that covers a few different areas. So anyway, thank you.
Thanks so much. I really enjoyed this talk, starting from the basics of quantum dots all the way to quantum computing. So I will stop the recording, and then if people have questions, please just jump in.